Okay, this is our second reaction type. Last time we talked about combustion reactions. Those are pretty simple, pretty easy to predict. You always get the same products. Today we're gonna talk about single replacement reactions. And single replacement reactions still not super difficult to predict, but they don't give you the same product every time. So let's jump right in. Let's start with the definition. A single replacement reaction is when an ion in an aqueous solution, just abbreviate solution, is replaced by an element. And when this happens, I'll give you an example. If I have magnesium chloride aqueous, and I add, let's say, lithium to that, and that's a metal, so lithium's probably going to be solid. We're going to have one of these two ions, right? We have magnesium, which is 2+, and we have a couple of chlorides that are each 1- in that aqueous solution, and one of those two is going to get replaced. And so if you think about it, it should make sense to you which one's going to get replaced. It's going to be the magnesium. And that is because the lithium is a metal and can make cations, positive ions. So it would make more sense for it to replace the magnesium. And by replacing the magnesium, now the lithium is paired with the chloride and the magnesium is by itself. So if that doesn't make sense, let's finish the reaction for you. So if the lithium replaces the magnesium, now instead of lithium by itself, I've got lithium chloride. And once again, we're going to look at the charges, +1 and -1 in this case, so I don't need any subscripts there. Now it's going to be the lithium that is aqueous now, so it's going to be AQ, or sorry, the lithium chloride that's going to be aqueous, so it's AQ. And it's going to be the magnesium that is by itself. And since it's a metal, all metals with the exception of mercury are going to be solids when they're in their elemental form at room temperature. So that would be our reaction. So I'm going to go ahead and just kind of clean this up a little bit, get rid of some of this stuff. We don't need to have the charges written anymore. We do need to balance. So right now it looks like we have chlorine that's not balanced, right? So I put a 2 in front of LiCl, which means I need to put a 2 in front of Li. Now, in this case, what I've done is I've replaced the cation, right? The magnesium, which was positive over here, got replaced, and now I've got a new cation in the compound in the aqueous solution. So we refer to this as cationic single replacement. And if we were to do an example of anionic single replacement, these are going to always involve the halogens. So group 17 only. We're not going to worry about any other anions from the periodic table like oxide or sulfide or phosphide or any of those. Just the halogens. And we'll make sense of why that is a little bit later, but let me give you an example. Let's say this time I have sodium chloride aqueous, and I've got some fluorine gas that I'm going to maybe bubble into that solution, to that aqueous solution. And what's going to end up happening is the fluorine, being a nonmetal, being a halogen, it has the ability to form anions, not cations, and so it's going to replace the anion in the compound. So rather than replacing the first substance, the metal, like we had, up above, this time we've got the nonmetal being replaced, the halogen being replaced by another halogen. And so if that happens, we should get, on the right side, sodium fluoride. And again, the compounds are always going to be aqueous, and we're going to get chlorine kicked out by himself. But if you remember, chlorine is diatomic, just like fluorine was over here. So whenever it's by itself, not necessarily in a compound, but whenever it's by itself, we have to put a 2 there. And you can always assume that the halogens, when they're in their elemental form, are going to be gases, although the bigger ones like iodine can be solid. We're going to assume for our purposes that our halogens, when they're in the elemental form, like fluorine and chlorine, we're going to call them gases. So go ahead and balance this one. Actually, I think this is a reaction very similar to one we had in our first day of notes. Looks like fluorine and chlorine are the unbalanced ones. That should be pretty easy to do. So if I just put a 2 in front of sodium fluoride and a 2 in front of sodium chloride, then that should be balanced. Okay, so the last thing we have to say about single replacement reactions is that it is possible for us to have a single replacement reaction that doesn't work. In other words, it doesn't happen. We don't get any products. We call it a no reaction. So we're going to say some single replacement reactions can't happen. And what we mean by that is, if I set up, let's say we go back up to, well, let's try a new one. Let's go with, let's say we have copper, which would be a solid, plus, let's just go back to sodium chloride aqueous. So if I put copper into salt water, essentially is what this is saying, what, if anything, is going to happen? And it turns out that this is a no reaction. And the reason it's a no reaction is if we look at what should happen, the copper and the sodium are both metals. So this is cationic single replacement, which reminds me I should have labeled this one up above. This was supposed to be labeled anionic single replacement when we had the 2 halogens replacing one another. But anyway, coming back down to this one would be cationic single replacement, because whenever I look at the thing that's by itself, the copper, that's the thing that's trying to do the replacing. So that's the thing that the thing that is like it in the compound, the other metal in this case, is what it's going to try to replace. So can copper replace sodium? That's a question that we have to ask ourselves. And the answer is actually found on the back of your periodic table, your yellow periodic table that I gave you, way back couple months ago. Has this thing on it called the activity series. So the activity series actually is there to predict whether or not a single replacement reaction will happen. So if I find copper on this list, copper is way down here near the bottom, right? And then if I find sodium, the thing it's trying to replace, it's much higher up. And so this reaction actually doesn't happen. And the reason it doesn't happen is because the activity series is there to help us predict reaction or no reaction for these single replacement reactions. And the thing that's doing the replacing has to be above the thing that it's replacing. So in this case, copper is trying to replace sodium, but copper is below sodium on the activity series. Okay, and so that can't happen. And so we would actually say that this is a no reaction. Or sometimes we'll just say NR for no reaction. So that's how we would predict a cationic single replacement. Anionic single replacement is actually just predicted from the periodic table. So I'll show you what I mean by that. If we do another example of anionic, so 2 halogens trying to replace, or one trying to replace the other. If I were to go with, let's say, barium barium bromide, BaBr2, aqueous, and we try to react that with, let's say, chlorine gas. So is that going to be a reaction or not? And what we do is we just look at group 17 of the periodic table, because our anionic single replacement reactions are always going to involve the halogens. And so here's just a, you can obviously look at your periodic table or the one on the wall, but here's a little piece of it. These are the halogens: fluorine, chlorine, bromine, and iodine. Astatine as well, but we don't typically use it. But the chlorine is trying to replace the bromine, right? Like those are the two halogens. Those are the two potential anions. And so the question is, can it do it? And the answer is yes, it actually can, because chlorine is higher than bromine. So the periodic table, group 17 of the periodic table, actually acts as a little activity series. So I would go ahead and say, yes, this reaction happens, and then I would go ahead and predict the products, which would be barium chloride, which would be aqueous, and bromine. And bromine is, it's a diatomic molecule. Bromine can be a liquid or a gas at room temperature, but just to keep things simple, we're going to say that all of our halogens are gases. I'm hiding behind the thing there. There we go. And then this one actually doesn't even need any balancing. So this one would be a reaction. All right, so I'm going to leave you with a couple practice problems here, and then you can work on a couple from a worksheet. Okay, so here are 3 for you to try. Make sure that you're recognizing whether they're cationic or anionic before you start. And of course, the way that you do that is you look at the element that's by itself to start with, that's not in the compound. If it's a metal, it's going to try to replace the metal. If it's a halogen, it's going to try to replace the halogen. So give these 3 a try. Take as long as we need for everybody to come to 3 answers, and of course balance them. Do assume that all of your compounds in your products are aqueous. Your metals will be solid. We're going to assume they're solid, and your halogens will be gases if they're in the elemental form. Okay, and then, like I said, balance. Okay, if you've had a few minutes to try these, let's go ahead with our answers. The first one is cationic. Aluminum is trying to replace cobalt. If I go to my activity series, I see that aluminum is actually above cobalt. There's aluminum, and there's cobalt down there. So this one is going to happen. And so I'm going to go ahead and predict what my products would be. So now I'm going to have aluminum nitrite, and that's going to be AlNO2 3 aqueous, and cobalt solid, going to be by itself. Balancing wise, I've got two nitrites on the left and 3 on the right. So I'm going to go ahead and use a least common multiple of 6. That means I'm going to need 3 cobalt, 2 nitrites, and 2 aluminum nitrites. And then I just balance my cobalt and my aluminum with 3s and 2s. Okay, the next one is gold trying to replace tin. Gold cannot replace tin. Gold is at the very, very bottom of the periodic table. Pardon me, at the very bottom of the activity series. That means it can't replace any other metal, so this one's a no reaction. So this one is just NR. And finally, will fluorine be able to replace iodine? And the answer is yes. Fluorine's at the top of group 17, so it can replace anything in that group. So I'm going to get MnF4 because the charge on the manganese is apparently +4. And the iodine is going to be by itself, but it is a Brinkelhoff. It's a, diatomic. So we got to remember that. And then to balance, I would just put a 2 in front of fluorine and a 2 in front of iodine.